Dear participants, can you hear me?
It's a yes on my side.
Okay, thank you. Okay, dear participants, welcome to 5th International Congress on Human-Computer Interaction, Optimization, and Robotic Applications. We are in session 1.1 now. Before starting the Congress, let me give you some information about the Congress. So, the Congress aims to bring scientists, experts, instructors, non-governmental organizations, and private sector representatives together to share and discuss theoretical and practical knowledge in a scientific framework. In addition to cutting-edge research paper presentations in human-computer interaction, optimization, and robotic areas, the Congress serves as a multidisciplinary platform for discussing current issues in the engineering areas. So, in this session, we have a special guest. Our keynote speaker is Professor Ömer Nezih Gerek. First of all, on behalf of organizing committee, I would like to thank you for your scientific contribution to the Congress and welcome to the Congress. Can you hear me?
Yeah. Yes.
Okay. Before starting his presentation, let me give you some biographical information about Professor Gerek. So, Professor Gerek graduated from the Electrical and Electronics Engineering Department of Bilkent University and received his PhD from the same university in 1998. During his PhD studies, he spent a semester at the University of Minnesota, USA, as visiting researcher. From 1998 to 1999, he was a technical researcher at the Swiss Federal Institute of Technology. Later, he joined Anadolu University. Currently, he is a full professor at the Eskişehir Technical University, Department of Electrical and Electronics Engineering. Professor Gerek has served as a member of Turkish Scientific and Technological Research Council Scientist Training Program for 2 years and a steering member of EECS Management Committee for 6 years. He is an IEEE senior member and area editor of Elsevier Digital Signal Processing, and he is in the editorial board of Turkish Scientific and Technological Research Council. He has authored several international book chapters and hundreds of index journal and international conference articles regarding the broad topic of signal and image processing, ranging from compression to classification, from machine learning to data analysis in various interdisciplinary topics. Professor Gerek, if you are ready, you can start your presentation.
Okay. All right. Thank you very much, Oğuzhan. Thanks for this kind presentation, and thank you very much for having me in this very nice event. Early in the morning, I thank the audience for participating here as well to listen. Let me try to make a screen sharing, start my screen sharing if I can. I think I did.
Yes, we can see your screen and you can start your presentation.
All right. Thank you very much once again. What I'm gonna make today is a very broad presentation regarding some of the experiences that I have achieved in the past decades, I would say. So it's about two-dimensional or multi-dimensional processing of one-dimensional data, or we can also put it as image processing for non-image data. So what is this all about, and what could be the significance of it, or why am I recommending this kind of an approach for the scientists? As Mr. Chairman has already indicated, my name is Ömer, and I'm from Eskişehir Technical University. So since we are an international audience, first let me make some commercial presentations like what is Eskişehir Technical University. There are some pictures over here. I'm in the electrical engineering department. We are a newly established and quite a small university. However, we do have an airport inside the university working on avionics, as well as, of course, all the other necessary disciplines. And as the name indicates, it's in Eskişehir. So here are some extremely nice photographs of Eskişehir. It's a very nice place, by the way. It's one of the most livable cities in the world, in top 10 every year. And this year it was the third. So it's quite a civilized place, I would say. And where is it? It's right in between Istanbul and Ankara, for whom you may be familiar with Istanbul and Ankara about Turkey. So after this much commercial, now let's go back to the topic, because you may already forget about the topic. So we are talking about higher dimensional, particularly two-dimensional signals. So what is the interest? Where does it come from? It is a visible interest because, as you can see, if you compare various aspects of signal processing, if you compare single-dimensional signal processing papers as opposed to multi-dimensional like image and video processing, the number of submissions, the number of publications, the number of publication medium, they are overwhelming in image processing as opposed to signal processing, let's say. Of course, image processing is also a signal processing, but there is an interest particularly for the images, as the numbers imply. And if there's more interest, then it automatically produces more tools. For example, the popular machine learning tools, of course. I mean, there is, of course, a lot of tools for classical image processing as well. But even with the machine learning, I just started typing some of the machine learning tools for images here. And I started writing these and I stopped. And then I started writing one-dimensional machine learning tools. What came to my mind is recurrent neural networks, LSTM, and their variants. But that was a few months ago. And then suddenly there's the concept of transformers arrived. Transformers and attention tools immediately generated interest to GPT, particularly ChatGPT, right? We all know about that. But the good thing regarding the image processing side is that they also work for the two-dimensional signals. Like there is from the same company of OpenAI, there is DALL-E and there is Midjourney, and over hundreds of generative adversarial network transformer models that I could spot immediately, particularly designed for two-dimensional signals, that is images. So the more interest, the more tools, right? And there are therefore better solutions. As of 2019, which is an old year, I know, but this ratio did not really change. The image processing toolbox of MATLAB is about 3 gigabytes, and computer vision toolbox is about 2 gigabytes. And if you add them up, it makes 5 gigabytes, as opposed to the signal processing toolbox, which is actually just below 2 gigabytes. So there are more tools to interpret and process two-dimensional signals. So let's convert our data into two-dimensional realm, if it's possible, of course. Can we do that is another question. Now, since ChatGPT have become an issue, it's a thing now, I recently made a chat with ChatGPT, and I asked about what it thinks about two-dimensional things, and it immediately started giving me answers like, "Oh, of course they are two parameter, two variable functions. like images, and there are many techniques and algorithms. Okay, it's a powerful and important tool for a wide range of applications. That's good. That's good. Okay, he knows this much. And then I said, do you think having a two-dimensional signal is advantageous over one-dimensional signals? It says in some cases, yeah, why not? It's maybe more advantages, but it must be noted that you must have the one-dimensional data or two-dimensional data first, and then apply your techniques accordingly, which makes sense, of course. That's what everybody does. Then I said, what about rendering one-dimensional time series in 2 dimensions? Interpret it like 2 dimensions. And then it started to fail. Okay, ChatGPT failed miserably here. For example, it said you can interpret a one-dimensional signal by plotting literally it on the screen and making an image, and say that that chart or scatter plot or whatever that plot is a 2-dimensional signal. That's a laughable and stupid thing, of course. That's not what we mean by making 2-dimensional interpretation of it 1-dimensional data. So he's wrong. And I say, well, that doesn't render into 2 dimensions. That's stupid. And of course, they apologize and then say, yeah, it does not actually render the data in 2 dimensions, of course. So what you can do is stack periodic segments of the data on top of each other. So now it knows a little bit about that one. And it also proposes like you can make heat maps or contour plots, and you can still interpret them as 2-dimensional, which starts making sense at this point. And I say that's a good idea because that's what we're talking about. Now, do they have advantages? It says, yeah, it may have advantages for pattern recognition and forecasting. For example, it may make it easier to apply 2-dimensional techniques to the data, such as image processing techniques. Now, that's a dangerously correct approach, I guess. So even ChatGPT is starting to learn about these things, I would say. So I said, can you think of some potential applications for such? And it provides like financial data analysis, weather forecasting, that's a good one. Energy consumption analysis, that's a good one. Medical data analysis, and that's also a good one, which are the ones that I want to talk about for today. It was a little bit, that's bad and good. You can interpret it in both ways. But it still provides some information, like you can use heat maps and things like that, which is, well, irrelevant. And then I say, yeah, for periodic signals, that may make sense. What about non-periodic signals, like electrocardiograph, which is quasi-periodic? The period is changing in time for heartbeats. And then it started saying you can just crop arbitrarily and stack and such. This is all laughable. Obviously, ChatGPT is not aware of how to interpret this kind of a problem. And I say, how about aligning the stacked rows according to the peaks of the ECG pulses? Yeah, you have to first identify the peaks, and then you can do that. I'm not sure whether it knows or answering me according to my suggestions. I'm not sure about that. So whatever. ChatGPT is slightly knowing these things, but he's not very good at this. So let's go to our perspective. The motivation started from the fact that most of the time we interpret the signal with the same dimension as the signal. So the signal or data dimensionality and sensor dimensionality are interpreted to be the same. For example, for audio signals, it is 1-dimensional. For photographs, it is 2-dimensional. For videos, it's 3-dimensional. But sometimes they are a little bit different. For example, hyperspectral satellite images can be interpreted as multidimensional because it has several visible bands, making a volumetric kind of an image. It's an image, but it's volumetric data. Computer tomography is totally constructed by 1-dimensional signals. Let me explain what we mean. You already know about this. The computer tomography is essentially taking a one-dimensional slice, because you cannot cut the head and look at what is inside, and you cannot take the picture like that. You have to do something, an indirect way of construction of an image. And the data that it's being constructed from is one-dimensional. It's a slice of a projection, a very narrow X-ray image, you can say. And then that very narrow X-ray image is being rotated, and you start obtaining some intensity profiles like these in the one-dimensional sense. So it's a lot of one-dimensional data from various directions, and then you have to reconstruct them using the so-called inverse radon transform. And the inverse radon transform, I don't know if it is being animated. It should be animated. Yeah, this one I hope. Okay, I hope, yeah. As you see, as it is rotated, it is obtaining one-dimensional projection data, and that projection data is called sinogram, and you can see it at the right-hand side of the image. But that is not the image that we're looking for. You have to use the inverse radon transform to construct what is inside this image. So this is just one example. Multispectral imaging can be considered as another interesting way of looking at the signal and sensor dimensionality difference. By the way, the original or the normal RGB image, even that one itself is multidimensional because it is hyperspectral. It only contains 3 spectra, but that's what it is. And then we have to visualize them as if it's an image. So native signal dimensionality is for the audio signals is the time domain, and for the photographs it is the space domain. For the voltage waveforms it is again the time domain, or for video signals it is time and space domain. So how can we convert one of them to another one? For example, in one-dimensional, when you look at it in a zoom format, you start noticing repetitions. So there are some periodicities. And what would happen if you just try to relate those relations in a different dimension? How can we do that? Well, what we can do is we can just cut according to the period and stack them or render them below one another and construct an image. If the original one was already periodic, then what we get is a 2-dimensional and sensible image-like a surface. We can say that an image is born at this point. So the critical questions, okay, that's good. It's very logical. Is this efficient in the sense of analysis, detection, data compression, etc.? And how do we find the period? How to determine the quasi-period? Is it constant? Those are the questions to affect the efficiency of what we can do. So according to my own experiences, here are some examples. This is the solar radiation data. That's a real data. I think it's every half an hour or something. Sometimes we measure them in more dense. There's a dashed and there's a red one. As you see, they are very close to one another. You cannot even separate that. You have to look very closely to see the difference between the 2 consecutive days of solar radiations. And what we can do then is again stack them below one another. And instead of this kind of a messy layout, which is quite difficult to interpret, analyze, detect, whatever, we can convert it to this 2-dimensional surface plot. This is a surface plot representation. You can also visualize it as an image. And it is clearly periodic because a day is always 24 hours. So this is, there's no need to check or see what is the period. It is 24 hours. So the horizontal direction is 24 hours. The others are the days. For example, this is for 1 year. You notice that the edges of this blob correspond to winter times where the solar radiation is low and days are short at both ends. And in the center, it's a summertime where the solar radiation is larger, higher, and the day durations are essentially longer. So this is a surface actually. And we can apply classical surface modeling, image processing modeling, etc., where we can apply the model at the left-hand side, which will leave us with some marginally small model errors. You cannot model with as few parameters. I think the left surface is like 4 parameters or something like that. It's a surface with 4 parameters. It's quite impossible to model the solar radiation with only 4 parameters if you interpret it in 1 dimension, right? So once you have the 2-dimensional model or 2-dimensional interpretation, you can have surface models, you can have 2-dimensional neural networks, you can have 2-dimensional Fourier and harmonic analysis, and 2-dimensional forecasting and prediction. Even perhaps 3-dimensional visualization could be possible. I mean, you don't have to stop, but it requires several years of data. Then it would make a volumetric 3-dimensional cloud like an entity, which is a very good model. So this, it's not even 4, it's essentially 2 models or 2 parameters or something like that. A is the variation in day and C is the variance of the day. And when you do it in the modeling sense, it will provide us with very few parameters, as you can see. So this model is, the 2-dimensional model is extremely efficient, and model orders are very small. And the solar radiation is also very good for making predictions, because, for example, today in the morning, it's a nice weather in Eskişehir. I don't know what's going to happen after afternoon, of course, but yesterday, these times, it was almost the same. But 1 hour before, it was not the same. 1 hour before, it was a little bit cloudy. Now it's sunny. So it's difficult to make a prediction from 1 hour before. I have to go 24 hours back, which increases the prediction model order to 24, even longer. But if I use 2-dimensional, 1 day before is only 1 pixel away from me. 24 hours before is only 1 pixel to the top of me. Like this previous day, same hour, to predict this hour today. So I can make better predictions with smaller model orders. I can do the same for neural networks. Again, because my upper pixel, lower pixel, or 2 days before pixel are very close to me. And it gives extremely accurate prediction results. The prediction is very good following for every hour in this kind of a 2-dimensional order, as opposed to even higher dimensional first order, 1-dimensional higher order predictions. Another experience that I had was regarding the power quality assessment, which is the line voltages that we have in our homes. It's 50 hertz in Turkey. And if you use some kind of a sampling, then what you can obtain is you can just stack 1 period of this 50 hertz signal down to one another, and then you again make an image. For example, at the right-hand side, part B, that is the image, and part A is the surface representation of those things. And over there, you start noticing some power quality problems, like there's a voltage sag, a voltage swell, or even I can say that the frequency of this signal is, the period is longer, so the frequency is slightly less than 50 hertz. And we have calculated, it's actually 49.9999. So 4 nines difference between the 50 hertz frequency and the frequency of this particular signal. Okay. So which one would you prefer? For example, for compression, well, instead of 1-dimensional compression of the data for storage purposes, or analysis of the voltage problems, of course, the 2-dimensional is good because you have a lot of tools over there, like a two-dimensional wavelet transform, two-dimensional edge detection kind of things. They will be all available to you immediately, and you will start making assessments which were previously impossible with the one-dimensional sense, or it would be too complicated to analyze in one-dimensional sense. Another example is here. These are all examples to show you that in real life, the two-dimensional methods are significantly more powerful than one-dimensional ones. These are all real examples. By the way, I also asked ChatGPT about what it thinks about this, the determination of frequency very accurately. And ChatGPT says that you should use one-dimensional, because in 2 dimensions, there may be noise and things like that. I don't know where he's inventing those wrong ideas from here, but it is insisting that you should use one-dimensional. And I said, I find it amusing. I mean, because the answers that it provides are a little bit inaccurate. And I said, what would happen if you use for half transform, radon transform to very accurately model the tilt angle, and then from there I would be able to find the frequency very, very accurately. All right, but it just didn't do that. That's a good news, actually. I insisted a little bit, and it eventually said, yeah, I agree. Very subtle differences can be achieved. And it also helps in compression as well. In compression, for example, the 2-dimensional concept is extremely valuable because we have JPEG, we have other image compression tools, as opposed to one-dimensional compression tools, such as MP3, for example, for audio signals. There is a huge signal-to-noise ratio performance difference. Another case, energy consumption of electricity. This could also be converted into 2 dimensions. Interesting. And it gives you quite a periodic sense, because every week we are consuming electricity at some point on Mondays, and weekly our profile is almost the same. And in general, if you average it for a city, for example, it makes a very smooth surface. And this surface can also be modeled very accurately, which means that at longer distances, time distances, like 1 year later, what's going to happen at this date, this hour, you can predict it very accurately, quite accurately. So this is just another example. It's the ECG data that I have proposed in the very beginning. It's also almost periodic, and if you stack over the peaks, it also provides a 2-dimensional situation in this sense. So why the success? The success comes from the fact that the correlations become close, making long-term strong correlations, short-term correlations. That is the result that I want to indicate. So if you have a period, for example, like this one, then A is the one that we have. A is essentially very closely related with D because of the periodicity. Now D is only 1 pixel up of our A, and E is only 1 pixel up of B, right? So that's a good thing. And even longer than that, 2 periods away is F, which is only 2 pixels far away from here, which reduces the model order of Rx, the autocorrelation model of capital N, which is a large number, which should be a very large number, into a 2-dimensional autocorrelation dimensionality with K and L to be very small. That is the idea that I want to emphasize over here. Instead of a covariance dimension of a very large number, you just reduce it down to a very small correlation case. So what can I suggest to the researchers? You may find other periodic, quasi-periodic cases, like the financial data, perhaps, right? ChatGPT was actually indicating that one. That's good. That's a good one. We can use wind speed. Wind speed is a little bit chaotic and it's not really periodic, but maybe for days it may make sense. What about 3 dimensions and more? And the most important thing is, since the literature is not really saturated, ChatGPT still cannot invent this idea. I mean, it's just not helping. So we still have some research gap room for human researchers regarding exploitation of this idea. And that concludes my presentation. Thank you very much. I may be a little bit late, but we have started a little bit late. I wanted to make it as fast as possible. Let me, okay.
Thank you very much for this great presentation. Dear participants, do you have any questions about the presentation?
So
okay.
If you want to just contact me about any kind of research possibilities, just type my name on the internet. You will be able to find my email immediately, and I'm always available. Thank you very much.
Okay. Again, thank you very much for your contribution to the Congress. If there are no questions, I am ending this session. Thank you very much.
Thank you.